Yeah, thank you, thank you. Yeah. Okay, so we are moving into the next part, that is, see, from this particular explanation of perceptron, we evidently prove that the perceptron can work for classification purpose, okay, and that is actually picturized or evidently represented with the example of an AND gate, right? But if you move into different other data like the AND gate, OR gate, see, you will get you can find a perceptron for AND gate and you can find a perceptron for OR gate. But when it comes to XOR gate, you will not able to find a perceptron that properly gives output as same as that of XOR gate. Will you be able to tell me why it is happening from this depiction? Is it possible to understand? So, what is a general representation of a hyperplane?
Excuse me,
Uh,
sir.
yeah.
Slides are not visible.
Oh, sorry, sorry, sorry. Okay.
No.
Is it okay now?
Yes. Okay.
Yeah. So, from this we can see that actually when we are having a hands-on workshop, we will first implement this on AND gate, then we will move to OR gate, then we will try with the XOR, and you will be stuck at that point. That is, you will not get the proper output for XOR gate, and then only we will move to this, as we are not having that time to explore it in a practical way. I'm just explaining these things. See, here for the AND gate, we are able to find a hyperplane, and for the OR gate also we are able to find a hyperplane. But in the case of XOR, the perceptron will simply fail. Okay, perceptron will simply fail, and this failure causes a big dilemma in the history of AI, and that age is actually called as dark age of AI or AI winter. Okay, it is caused due to this particular problem. That is, even a small problem like XOR is not solvable with a perceptron. Okay, not solvable with a perceptron. Then people start criticizing this neural network. They are not giving much fund for the researchers in neural network, and the AI domain itself become stuck. And as I said, that age of AI is actually called as dark age of AI or AI winter. Now let me explain what is the problem this with this XOR gate. Okay, so it is nothing but, see, what is the general equation of a hyperplane? It is y is equal to sigma wi xi plus theta, right? Sigma wi xi plus theta. So in the case of a single feature, it will be like w1 x1 plus theta. For two features, it will be w1 x1 plus w2 x2 plus theta equal to 0, right? And for three features, w1 x1 plus w2 x2 plus w3 x3 plus theta equal to 0. So as the number of features increases, the nature of the hyperplane is actually also changing. But keep in mind, all these hyperplanes in different dimensions are linear in nature, right? All of them are linear in nature. So in particularly in the two-dimensional case, this particular hyperplane is actually having a representation very similar to ax plus by plus z is equal to 0, right? So in a two-dimensional case, we are actually finding a hyperplane as a line. And in the case of AND gate and OR gate, you are able to find this hyperplane or a line very specifically with the given distribution of data, right? These are the negative distribution. This is the positive distribution. you can find a line that separates. Here, this is the negative distribution, this is the positive distribution, you can find the hyperplane. But in the case of XOR, will you be able to find such a line? Just think of it. Will you be able to find such a line? Is it possible? Is it possible to find such a line? Can you draw a line, and after drawing that line, the white point should be on the one side and the black points should be on the other side? Is it possible? Is it possible? I'm not getting any answer from your side. Consider it as a puzzle. So just I'm just asking you, are you able to solve this puzzle?
So first impression give that it is not possible.
Yeah, definitely it is not possible. That is the correct answer. Because the problem itself is called as, this problem is a non-linear problem. Okay, non-linear problem. Okay, or it is not linearly separable. Okay, the problem is not linearly separable. So whatever it is, the perceptron will fail to find such a hyperplane for the situation. Okay, and this marks a big event, marks as a big event in the history of AI, because it started the age of dark AI. Okay, age of dark AI. And after some years, people are working on it, people are doing research on it, then they will come up with a new structure of artificial neural network, which is quite different from perceptron, and it is called as a multi-layer perceptron. Okay, it is called as a multi-layer perceptron. Okay, and what is happening in multi-layer perceptron? It is nothing but it is a network of perceptron which is arranged in a feed-forward manner. Okay, which is arranged in a feed-forward manner. What do you mean by feed-forward manner? Because one layer, the neurons are arranged in, or the perceptrons are arranged in different layers, and the output from one layer will be served as an input to the next layer, and there won't be any kind of back connections. Okay, the current connections. Okay, that is why it is called as a feed forward network. And the number of hidden, the layers, the number of hidden layers, this layer is actually called as a hidden layer. The number of hidden layers and the number of neurons in each hidden layers are actually uh, purely arbitrary. Okay, there is no rule for finding such a number of hidden layers and neurons. Okay, now we can move to the XOR problem, and we are going to explain how the XOR problem can be solved with multi-layer perceptron. Okay, and in different videos, in different explanations, textbooks, you can actually find different ways of explaining this particular situation, and most of them are actually not convincing for me. So what I did is I have created my own way for explaining this concept. So what I am doing is, see, consider we are having our data, XOR data, and the XOR data is 0 0, the output is 0, 0 1, the output is 1, 1 0, the output is 1, and the 1 1 is the output is 1. And if you see the distribution of data, it is purely non-linearly separable, right? Non-linearly separable. So I request you responses, prompt responses, if I ask something, so that we can make it more engaging. Okay, so please be responsive. Okay, see, now the trick I'm doing here is, see, from this data I can clearly say that the data is not linearly separable, right? But what happened if I just ignore this observation? What happened if I just ignore this observation? So that is the observation 0 0. I'm just ignoring this observation. And if you consider rest of the data, Is that linearly separable or not? Will it be linearly separable or not? What do you think? Can anyone tell me? If I ignore the first observation, that is 0, 0, 1, and we are just taking the rest of the observations 0, 1, 1, 1, 0, 1, 1, 1, 0, and if we plotted the data over here, these are the negative observation and this is the positive observation. Sorry, these are the positive observation and this is the negative observation. Is it linearly separable or not?
Yes, sir, it would be. It looks like.
It is linearly separable. So definitely you can find a perceptron O1, right? Okay, but one of the problem with O1 is this observation. If you give input to O1, this observation will be misclassified as 1, and all other observations will be properly classified. So that is the case of O1. Okay, so O1 is a perceptron. I have learned from the data 0, 0, 0, 1, 1, 0, and 1, 1, and finally on giving the inputs, the 0, 0 will get a incorrect prediction. That is, actually it is 0, but O1 will predict it as 1. In all other cases it will be 0. It will be right. Okay, and in the second stage what I am doing is I am just ignoring the last observation, that is fourth observation. That is, I am just ignoring this observation. Is that linearly separable now? What do you think? Is that linearly separable? And will you be able to find a perceptron there?
Yes.
Yes. So you can find a perceptron for this much data. Okay. So this will be a negative observation. These two will be a positive observation. And definitely 1, 1 will be misclassified by O2. This is actually 0, but it will get misclassified as 1. Right? Now consider this structure, that is the inputs x1, x2, okay, the inputs x1, x2 is giving to this nodes and it is directly channeling to O1 and O2, right? So O1 will give the outputs like 1, 1, 1, 0 for the input 0, 0, 0, 1, 1, 0, and 1, 1, and O2 will give the outputs like 0, 1, 1, 1 for the input 0, 0, 0, 1, 1, 0, and 1, 1, right? Okay, so at this point for the first combination you will get the output 1, 0. For the next data you will get the output 1, 1. For the next data you will get the output 1, 1, and for the next one you will get 0, 1. So what are the possible inputs towards Z? It can be either 1, 0, 1, 1, and 0, 1, 1, 0, 1, 1, and 0, 1. And for 1, 0, for 1, 0, it is the output for 0, 0, right? What is the actual output? We are mapping that here, that is 0. And for 1, 1, this 1, 1 is obtained from the combination 0, 1 or 1, 0, right? And for both 0, 1 and 1, 0, the output will be 1. Okay, the output will be 1. And for the last case, that is 0, 1, 0, 1, the output will be 0. Now, if you look into this data, this will be linearly separable, right? This data will be linearly separable. How you can understand that? See, for 1, 0, it is 0. For 1, 1, it is 1. And for 0, 1, it is 0. And clearly it is linearly separable. Okay, understood? Now consider the entire network together. What will happen for this entire network? If you consider the entire network together, what will happen? If you give the input 0, 0 here, you will get the output 1, 0, and on getting 1, 0 from Z, you will get the output 0. And for 0, 1, you will get the output 1, 1, and for 1, 1, Z will output what? 1. And for 1 0 also, for 1 0 also, the output from O1 O2 is 1 1, and on giving 1 1, the output will give, the Z will give the output 1. And for 1 1, the outputs are 0 1, and on giving 0 1 to Z, it will give the output 0. So for all this data, you will correctly get all the outputs, which is very clear to the XOR outputs. Okay, so the perceptron with one neuron is not capable of handling XOR problem, but when you cascaded this perceptrons as different layers, then that structure together is able to solve the problem of multi-layer perceptron. Okay, so this is called as the input layer, this is called as the hidden layer, this is the output layer. Okay, hope you understood how the structure of multi-layer perceptron with the given set of weights are able to solve the XOR problem. But you just forgot how I have arrived at this weights. Okay, I just want to convey you that with this structure, with this given set of weights, with this structure and with this given set of weights, you will be able to handle XOR problem, right? You will be able to handle XOR problem. And the creating the structure of a neural network is a programmer's responsibility or a user's responsibility, but arriving at the proper set of weights, arriving at the proper set of weights for a problem is something different. It is not the same story as I said to you. Okay, so from this example, I just want to convey you that XOR problem can be handled with this structure and the set of weight values I have assigned to it. Okay, and the intuition behind a hidden layer is that, see, the intuition behind a hidden layer is that as the hidden layers increases, as the number of hidden layers increases, okay, if there is no hidden layer, then you can only handle the linear problem. But as the number of hidden layers increases, we can say that we will be able to tackle more complex decision boundaries. Okay, we will be able to tackle more complex decision boundaries. Okay, so that is why here depicted. See, this is a simple multi-layer perceptron. Okay, this is a simple multi-layer perceptron. That is one simple neural network, and the next one is actually called as a deep neural network. So, what is the difference you can observe from these two images? What is the difference? In
More
simple
hidden
neural network,
layers.
yeah,
Hidden layers.
will be more. Yeah, in simple neural networks, the number of hidden layers will be limited, and in deep neural network, there will be more number of hidden layers. Okay, there will be more number of hidden layers. So the intuition is that as the number of hidden layers increases, as the number of hidden layers increases, the learning process happening inside that network will be more. Okay, so it can tackle more complex problems. So that is the one property of a deep neural network, that is it should have more number of hidden layers. And the second property of a hidden layer of a deep neural network is that, see, here in the case of machine learning, as I said in the example of PK, how PK perceived a shirt, is PK perceived a shirt as shirt itself? How PK perceived the shirt, or how PK interpreted the shirt?
After training,
Yeah, after on training, what all things PK considered for distinguishing a shirt?
different features,
Yeah, different features, right? That is the color, the type, as well as the
size.
size. So why a machine learning model cannot accept the input as such? Because the clarity or the performance of the machine learning models will directly depend on the features we are extracting from it. That is a big limitation, right? Because if I ask you, how can I classify, how can I consider the features to classify a set of images of apple and banana? What all features I can consider? Can anyone tell me? What all features I can?
Color and
Color and
size.
size.
Color and size, right? But if I ask you, what are the features I can extract to classify the strawberry and apple?
Size and taste.
Size and taste. If I ask you you can classify, or how can you extract the features to classify the images of two film actors, say Mammootty or Mohanlal, or Vijay or Surya, or Shah Rukh Khan and Amitabh Bachchan? What all features you can extract? Is it possible to tell me very easily?
That's not easy.
Not easy.
More features
That
are
is,
needed.
yeah, that is the limitation of machine learning. That is, we have to explicitly identify and extract the features for our problem from our data to build a machine learning model very in a very good manner, right? But in the case of deep neural networks, that problem is actually solved. That is, the deep neural networks or the deep learning networks are capable of extracting the features, okay, extracting the features automatically from the inputs, okay, automatically from the inputs, okay. So how can you distinguish a machine learning and a deep learning task? What are the two properties we should highlight? The deep neural networks or the deep learning networks will have more number of hidden layers, and it is having a special property called automatic feature extraction. Automatic feature extraction, okay. And before moving into the detailed aspects of deep learning, I just want to convey you how uh, the backdrop, the weights are actually getting uh, calculated in a multi-layer perceptron. For that, we are simply using an algorithm called backpropagation learning algorithm. And the idea of backpropagation learning algorithm is very simple, and it is also in same way it is also complicated in terms of mathematics. The layman idea is very simple. That is, see, suppose you are having, okay, a neural network like this, okay. So I'm getting an output y cap, and one expected output is y, and that y is 2. The inputs are 135, okay, and this y cap is actually zero point 0.3, okay, and w1, w2, w3, w4, w5, and w6, okay. These are the weights. So the situation is that I'm giving an input 135 and I'm expecting an output 2, but the neural networks is actually giving an output zero point 0.3, and there is a difference between this zero point 0.3 minus 2 whole square. So some error value will be there, right? This is what we are calling as error. I just want to ask you, who is responsible for this error? Can you tell me who is responsible for this error?
So is it weight?
Yeah, that is the way the error value is actually impacted with the incorrect values of W1, W2, W3, W4, W5, right? And W6. Is it clear for you? We are getting an error at y cap because of the incorrect values of W1, W2, W3, W4, W5, and W6, right? Is that clear?
Yes.
Yes, sir.
And how can you reduce that error? How can you reduce that error? By adjusting the value of W1,
Updating
W2.
weights.
Yeah, by updating the weights, right? So I can say that this error is actually a depending on these variable, or I can simply say that this error is a multivariate function of W1, W2, W3, etc. up to W6, right? If I tell so, are you clear with that?
Yes, sir. Yes, sir. Yeah,
Yes.
multivariate factor.
Yeah. So if this error is totally caused by each of this ways, what is the contribution? How can you evaluate the contribution of each of this weight towards this error? Just go through the things we have discussed. If this function, this quantity E is observed through the function S, okay, and this function is depending on W1, W2, etc. up to W6, how will you calculate the change happening on this E with respect to each of this W1, W2, W3, and W6?
By derivation, sir.
Error.
Exactly. That is, we have to take the partial derivative of E with respect to W1. We have to take partial derivative of E with respect to W2, and we have to take partial derivative of E with respect to W6, right? So you got the contribution of each of this variable towards the error, right? So some variables are contributing more and some variables are contributing less. Now I have to adjust the weights, right? How can I adjust the weight? Wt plus 1 as Wt minus this dou W by dou E by dou Wt. And this is what we are calling as gradient descent. This is a very simple concept, that is, if this is the optimal point, okay, if this is the optimal point and you are at this point x0, it is evident that moving this direction, the change happening will be high, right? And moving this direction, the change happening will be less, right? So what is the change? It is nothing but the derivative, right? So if you move opposite to the increasing value of the derivative, you can arrive at this optimal point. Okay, you can arrive at this optimal point. That is why we are updating our x0 as x0 minus the derivative of that function with respect to x0. The same technique is used here. Okay, the same technique is used here. The partial derivative, which represents the contribution of that particular weight towards that error, is calculated, and we will subtract that particular partial derivative from the current weight to go towards the optimum value for each of these weights. Okay, so this is the overall idea of backpropagation algorithm. See, now you can look into this animation. See, I will just show you. See, currently the inputs are given. Each of the time, the nodes are calculating the values, and finally you are getting a value y, and it is compared with z, calculating the error and backpropagating to adjust the error using the equation like this. Is it clear now?
Yes, sir.
Okay, fine. This is a simple concept. There are a lot of mathematical stuff behind it. I will show you this. See, these are all the mathematical things that is happening behind this back propagation algorithm, finding the derivatives, finding the updated weights. A lot of things are actually happening here, but I'm not going to explain all these things. And I just want to convey two more things up as a part of this. Then we can move to the one of the major deep learning algorithm, which is called as convolutional neural network. So I have taken a particular technique called gradient descent, right? Gradient descent. for arriving at the optimal values for the weights. And similar to gradient descent, there are other mathematical techniques: stochastic gradient descent, ATAl, stochastic gradient descent with momentum, mini batch. A lot of optimization techniques are there, and each of them are actually having difference in their mathematical formulations. But the idea is same: just update the current weight with the gradients. Okay, with the gradients, and the calculation of gradients are different in each of this equation. Okay, and these are all different optimization function. And different from that, you have to familiar about two more terms, that is activation function. The activation function is for, we explained in the example of perceptron. There we have used a unit step function, right? But some of the situations, we, instead of classifying an input, okay, instead of classifying an input crisply as 0 or 1, crisply as 0 or 1, we need to to find the probability towards that particular class. Instead of that, 0.8 chance towards the 0th class, 0.2 towards the class 1, right? In that situation, you can simply make use of sigmoid activation function. Okay, sigmoid activation function. So whatever value, the peculiarity of sigmoid is that whatever value you are obtaining at this point will get squashed in between 0 and 1. Okay, will get squashed in between 0 and 1. That is, you will get a probability of an input towards a particular class with the sigmoid activation function. Then there is an alternative which is called as tan h. It will squash the value between -1 to 1. Then ReLU is another activation function which is very widely used in deep neural network to get rid of an issue called vanishing gradient problem. I will explain that what is vanishing gradient problem, because of the non-linearity of this ReLU activation function, as well as the non-differentiability of this function. It can actually tackle the vanishing gradient problem. And one more function you have to keep in mind is loss function. As I said, the output obtained is y, and the output y cap, and the actual output is y, right? So you have to find the difference between these two things, right? How, in what all way we can find the difference? I can simply take the absolute value y minus y cap, or I can take y minus y cap minus y whole square root. Likewise, we can have different ways to calculate the loss, that is the difference between actual value and the predicted value. And for that only we are doing the optimization to reduce that error. Okay, so the most widely used loss functions are binary cross entropy, categorical cross entropy, sparse cross entropy, and in the case of regression problems, it can be MSE, RMSE, MAE, MAP kind of stuff. So all these things are actually loss functions. Okay, so telling about a neural network, what all terms should come in your mind is the inputs, the weights, the layers, the neurons. Okay, the neurons, then the bias, the optimization function, okay, and the loss function, then activation function. Okay, activation function. So these things should be clear in your mind when you are thinking about an artificial neural network. Okay, hope you have understood what I have conveyed so far, right? And I know it is a very quick explanations. We need actually a 1 day session for covering the entire topic in a very slow phase, but we have to make it in a 2 to 3 hours. That is why I'm moving in a very fast pace. Okay, so if you have any doubts, you can ask. Otherwise, we can simply discuss about the last topic, which is called as convolutional neural network.
Sir, what is the difference between categorical cross entropy and sparse categorical cross entropy, and how do we decide which one to go for?
Yeah, so I will tell you that because sometimes, see, in the case of a in the case of a classification problem, okay, sometime, see, yeah, in the case of, where is that point? Yeah. So in the case of classification problem, some are actually called as if the classes are A, B. Okay. Now then we are called it as a binary
Binary
classification.
classification.
Binary classification.
Yes, sir.
If the outputs are A, B, C, and D, okay, A, B, C, and D, then it is called as what?
Multi-class classification.
Multi-class classification. So in this case, as A and B is there, we will encode these outputs as 0 and 1. Simply, one class below is represented as 0 and the other class is represented as 1, right? So in the situation, we will use binary close entropy. Is that clear?
Yes, sir.
Yes. But in the case of A, B, C, D, you have two choices. You can use a label encoding, then it will be 0, 1, 2, 3. Okay. Or you can use a one hot encoding, that is for class A, it will be 1, 0, 0, 0. For class B it is 1,
0
0,
1 0
0,
0.
0, 1, 0, 0, 0, 1, 0, and
Yes.
0, 0, 0, 1. Okay. So if you
Yes.
are using this convention, use sparse categorical cross entropy.
Yes.
And if you are using this convention, then you can use categorical cross entropy. Is it clear?
Sir, but in this deciding 0 1 2 3,
Yeah.
what difference will it make if we choose either of them?
Yeah, it is having a difference because if a single neuron is using, okay, for the output, that single neuron need to be output 0, 1, 2, and 3, right?
Yes, sir.
So if you're using a ReLU activation function, okay, sorry, not ReLU. If you're using a simple
Sigmoid.
unit
Okay.
step function, you can simply output 0 and 1.
Hmm.
If you use a sigmoid activation function, what will happen? The value will be in between 0 and 1. Okay. So for a binary classification, it is not a problem. But in the case of a multi-class classification, how a neuron can actually out 0, 1, 2, and 3, it is more complex, right?
Yes, sir.
So what we are doing is, instead of keeping one neuron, we will keep 4 neurons at the
Output layer.
end, output layer. Then each of this neuron will output a probability between 0 to 1. Okay. So if it is 0.5, if it is 0.1, if it is 0.9, and if it is 0.2, what is the maximum value?
0.9.
0.9. So you can conclude that the input belongs
2.
to 2. So to compare the lows, you have to keep the actual label as how 0, 0, 1, 0, right?
Yes,
Then
sir.
only you can calculate the lows. So if you are keeping your structure like this, okay, if you're keeping a structure like this, you can simply use for what? Categorical close entropy. But you can somehow manage to get output like this 0, 1, 2, and 3 by keeping a ReLU activation function or a linear activation function. In that case, you can make use of what? Categorical, sorry, sparse categorical close entropy. Is it clear?
So, sir, for always for multi-class classification, we should or we will have to use as many number of neurons in the last layer as many are the classes into which we want to classify.
Yes. Exactly. That is the proper way of doing it.
And in case if such is not done, then what will be the consequences?
Because it will take more time to converge. The
Okay.
loss calculation will get altered, so you
Hmm.
will not get the proper weights even after more number of iterations.
But then will it not impact the connectivity of that entire multi-layer perceptron or the multi-layer neural network?
I didn't get that question
I
actually.
mean, if we use only one neuron in the output layer,
Yeah,
and in place of that, right now we are using, for example, four neurons in the output
neurons.
layer.
Yes. Yeah.
So when we are talking about error back propagation and things like that,
Yeah.
will there be no change in the dynamics of the network?
No,
If
no,
the
no. It is actually the last layer.
hmm,
If you are using only one neuron,
hmm.
if the previous layer is having m neuron, the
Yes,
weight
sir.
matrix will be m by 1. If you are using n neurons at the end, it will be m by n. That won't make a big change in the computational cost.
Okay, sir. Thank you.
Yeah. So we can move to the last part, that is the convolutional neural network.
Sir,
Yeah.
sir, I have one doubt, sir. So when we
Yeah.
are
Tell me.
going for multi-layer neural networks, we are based upon all these things are based upon the weights that we are adding to that network.
Yeah.
Suppose if will there be any possibility that these weights will change in between and our accuracy will get affected, sir? Then is there any possibility that we will be able to identify where the weights have been got disturbed so that my accuracy I'm not getting it as per my requirement?
Yes, 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 yes. There are uh, method called gradient tracking. Okay.
Okay, sir.
Or there is something called gradient explainable things. With that, actually, you can track where is the gradients are. Actually, you need not to do that one thing, okay? Because
Yes.
all the weights will get updated in a proper way if the data and other configurations are clear. Otherwise, entire weight will get affected.
Suppose if we are not able to get the accuracy as what we are expecting,
Expected. Yeah.
then in that case, what are the possibilities that we can
You can
troubleshoot?
try. Yes, yes. The first thing you may be the first thing you can do is you can simply increase the number of hidden layers.
Okay, sir.
Okay, because whenever you are not getting a proper accuracy for your particular data, the problem is that the data will be more complex, or it is having no more complex non-linear boundaries, right?
Yes, sir.
So you can increase the number of hidden layers to tackle that problem. Okay, and there is a theorem called theorem says that whatever is actually doing with a deep neural network can be done with a shallow neural network. Shallow neural network is nothing but a neural network with one hidden layer, but
Okay.
by increasing the number of neurons. Okay,
Okay.
but the problem is that if the deep neural network is applied, we may be able to tackle that problem in 100 iterations or 200 iterations. But if you if you're keeping the number of layers as one and simply increasing the neuron, instead of this 100 iterations, you maybe go for 1000 or 10,000 iterations. So the convergence time will be more high
Hmm. Hmm.
when you are using shallow neural networks. Okay,
Okay.
and one more situation is there which is called as overfitting. That is, at the training time you may be getting good results, but while testing the data you will not get the proper
Yes, sir.
performance. That is what we are calling as a say overfitting situation. So what is the problem for that is the bias and the variance in the data.
Okay, sir.
Okay, maybe like if you are training a dog cat classifier, okay, and
Yes.
on considering the data for dog, you are only taking the Dalmatians.
Hmm.
So what will happen? The variance within the data is not there, right?
Yes, sir.
So it will the machine will only learn to identify Dalmatians. Even if you give a German Shepherd or a Doberman or a Pit Bull, it will not consider that input as a dog.
Okay.
So that is the case of overfitting. That is due to the bias and variance in your data. So
Mm.
you can change the model parameters as well as you can clear your data to get the better results on your machine learning and deep learning models. Okay.
Okay, sir. So once this is done, sir, generally we will be going for optimizing techniques. Why we will do that, sir?
uh, because maybe if I try with 100 layers, okay, each
Okay.
having 10 neurons, you will get
Mm.
good answers, right?
Yes, sir.
But the size of the network is too high.
Mm.
Maybe that much layers are not enough, not needed for tackling such a problem.
Hmm.
So by reducing the number of layers, by keeping the same accuracy, you can optimize your model, right?
Okay, sir.
That will help you to deploy your model very fastly. That will uh, help you to transport your models very fastly. Okay, so
Okay.
we always focus on keeping the minimum number of hidden layers by getting the maximum accuracy.
Okay, sir. Okay, sir. Thank you, sir.
Actually, how do we know the converging point of an artificial neural network?
Because the loss will be minimum. If the
Okay,
loss
minimum.
if the
Uh,
loss is becoming to zero,
is
what
that condition is possible? The loss is zero.
a
Is
zero
that
is
condition?
zero is possible if the data is so pure. That is, if you keep a set of dogs, sorry, a set of crows and get a set of parrots, is there any
Okay.
confusion between the data?
No.
No. So at that cases, you can converge it into zero loss. That is accuracy one.
Okay.
Yeah.
Okay. So depending upon the data set, the conversion point is decided.
Yeah, that is. You have to keep in mind that two words, that the bias and variance.
Okay.
Depending on the bias and variance in your data, you can actually
Okay.
manage to keep what value the loss should be there, what value the accuracy should be there. And we are
Okay.
in a real time situation, we are actually not expecting 100% result, because if it
Okay.
is 100% result, as I said in the previous day, that is a well defined problem, right?
Okay.
There is no need to use machine learning there.
Yeah. Yes. Yes.
So somewhere there is a kind of uncertainty, then only we need to go for machine learning. At that point, we cannot tackle that problem in a 100% way. Okay.
Okay, sir. Okay.
Yeah. So let me explain the last part of our talk very quickly. That is, we are going to discuss about convolutional neural network, which is a kind of deep neural network having the property of automatic feature extraction. Okay. So as I said in the previous example of the PK, if you want to classify uh, an object as a shirt or not, first you have the shirt, you have the extract the features, then that features are actually given to the machine learning model to decide whether it is a shirt or not, right? But it is a very difficult task, that or it is a very cumbersome task to find out the exact features which is relevant for a particular problem. So this convolutional neural networks are actually solving that issue with a mathematical operation called convolution. Okay, so what is the idea of convolution? It is nothing but, see, I will explain with an example. Suppose I want to predict whether there is a beak at a particular region in this image. Okay. So what I will do, I will simply take the region as an input. So this region is actually a collection of pixels, right? That pixels are the features I am taking, and I am giving that pixels directly into a neural network and predicting whether there is a beak or not. I'm just calling this as a beak detector, and it is possible, right? If this is a linearly separable problem, then we will be able to identify a neural network that can classify the given region as a weak or not. Okay, suppose I want to detect weak at the another region of the image, because here in this first input, the beak is on the left upper left corner, and here it is in the middle, right? So how can I do that? I'm just taking the input from the middle. I'm again creating another perceptron or another neural network to find the middle beak detector. Okay, so how many such beak detectors I need to create to tackle the presence of beaks anywhere in the input image? Will it be complex? We need to create n number of beak detectors, right? So instead of that, what we are doing is we will simply create one beak detector, okay, one neural network or a beak detector, okay, and we will move that beak detector around the image. That is, we will start from the top left corner, then we will move to right, then right, then right, then right. On reaching the end of that row, we will move, come down to the left, and again traverse through all the regions of the image and detecting whether there is a beak or not. Okay, so this detecting module is actually called as a filter or a kernel. And how this detection is happening, that is the core idea of convolution. A convolution is a mathematical operation to find the correlation between two patterns. Okay, correlation between two patterns. See, so this is our input image. Okay, consider this is our input image, and this is the pattern need to be checked whether it is present or not. Okay, and this is called as a kernel. Okay, the kernel. Now what we are actually doing is, see, to find the presence of this particular pattern in the input, we will first overlap that input in the particular region, and we will find out the dot product. Okay, that is 1 into 1 plus minus 0 into minus 1 plus 0 into minus 1 plus 0 into minus 1, etc., up to 1 into 1. Then you will get a dot product 3, right? So on performing convolution with this filter on the region of this image, you will get the output 3, and you are doing the same operation on the next region, then you will get another output. And the choice of taking this region is actually called as stride. So if you are choosing the stride as 2, you can move like this, you can jump 2 columns apart. Okay, and for the explanation, I'm just simply taking the stride as 1. See the first convolution value, the second convolution value, the third convolution value, the fourth convolution value. Here likewise, we will traverse through the entire region of the image, then you will get values like this, right? And this is actually called as an activation map, the output from the convolution operation on an image. Okay, then what is the significance of this activation map? See, can you just observe the bigger values obtained in the activation map? The bigger values obtained in the activation maps are 3, right? And these regions, what about this region? In these regions, actually you can find the presence of that particular pattern. If that pattern is not at all present, see here the pattern is not at all present, right? Okay, or here the pattern is not at all present, right? That there you can see the values -3. Okay, and here if you look into this region, the pattern is partially present, right? So here you have the value 1. So what is the implication of this activation map? The activation map carries the information about the presence of a particular pattern defined by a filter on the input. Okay, hope it is clear for you, right? So an activation map carries the information about the presence of the particular pattern defined by a filter in the input image. Now, after detecting the presence of a particular package, I will repeat this for the another pattern. See, here I am taking a vertical line. Previously, I am consider a horizontal line. Then again, I will get the activation map. Okay, and you can do this for n number of filters. Okay, you can do this for n number of filters, and together these activation maps are called as activation volume. Okay, activation volume. Okay, so as a result of convolution operation on the input image, you will get an activation volume at this point. Okay, and you will get an activation volume at this point. And the significance of this activation volume is it will carry the information regarding the presence of different patterns defined by a filter on the input image, right? Now, do we really need to keep this much activation map values to the next operation? Because instead of keeping the entire activation values, you only need to keep the maximum values, which is with this operation is called as max pooling. So we may think like on performing this max pooling, we are losing some kind of information, right? But it is nothing like that. It is only having the effect of just a subsampling. Okay, subsampling. The overall information will be retained, but it is getting reduced into smaller size. That is the only impact we have. Okay. Now after this, again we will give that activation volumes. Okay, activation volume as an input to the next convolution layer. Okay. So what is the significance of applying again the convolution layer? Can you just think of it? See, suppose I will give an explanation here. See, suppose our input is having a bigger diagonal stalk, that is 1 1 1 1 1. Okay, so on after doing the convolution, you will get a value 3 with this align. Then you will get a value 3 with this, and you will get a value 3 with this, right? Then if you perform a convolution on these three, you will get a bigger value 9 here, right? So what is actually indicated with this 9? If you're getting a 9 here, you can understand that there is a bigger diagonal line is present over the actual input. In the actual input, there is a bigger diagonal line, right? So what is the intuition behind adding more convolution? At the first convolution layer, it will simply learn about simple stocks, small stocks. After that, it will learn about the bigger patterns which made up of the stocks. Okay. Then if you apply again convolution, the bigger patterns will get joined together to get the shapes of objects. Then on applying in another convolution, the object parts will get combined to form the objects, right? In this way, on applying multiple convolution max pooling, layer, at the end of the convolution layers, you will get a set of values. You will get a set of values which represents the presence of a particular shape. And with that features, the fully connected layer, that is similar to a fully feed-forward network, will classify our input into a particular class. Okay, so this is the core idea of a convolutional neural network. And with this convolutional neural network, you can extend the concept to perform semantic segmentation, where we can exactly find out in which all pixels the object are present, the localization, okay, where the object is exactly present instead of simply classifying it as cat, and object detection is multiple localization happening on it, the instant segmentation, right? These things can be done. And with this essence itself, the deep generative models are also introduced, which is called as deep autoencoders, generative adversarial networks, and all. Okay, so you will get clear explanations of these things in the future classes. Okay, so hope you got a proper idea of how this deep neural networks are actually happening. I can give you, I can show you some examples of.
Sir, could I ask a question, please?
Yes, yes, ma'am.
Sir, does subsampling also lead to any information loss?
Yeah, sometimes it is actually making some issues, but in a normal perspective, it is not making any issues. But the hierarchical relationship between different objects within an image is important. This subsampling will make issues. I will show you that example. See, capsule networks. So this is a special kind of neural network which is called as capsule network. Okay, which is introduced by one of the prominent deep learning guy, Jeffrey Hinton, who is the actual father of uh, artificial neural network. Okay, so Jeffrey Hinton says that due to the issue in max pooling, see, the neural networks will get confused. The neural networks will get confused because if you train your face, okay, if you train your face with a neural network, okay, capsule network. Give an example. See, so as I explained, the CNN, if you are giving an image, okay, if you are giving an image, the convolutional neural networks are actually learning about small patterns at the first layer, then the stalks, then the object parts, then the objects as it is, right? So it will only check for the presence of different parts within the image. Okay, so even if you alter these parts, okay, even if you alter these parts like this, okay, even if you alter these parts like this, if you give this as an input to the convolutional neural network, the neural network will be able to classify it as that particular person. Okay, so this is because of the one of the major drawback in the max pooling. Okay, that is actually pointed out with by the Jeffrey Hinton itself. Okay, so he proposed another neural network which is called as capsule network to handle this problem. That is the one of the major limitation or the one of the major issue with the max pooling, and we always use another alternatives like average pooling kind of stuff for handling this issue. Any other doubts?
Sir, could
Sir,
you?
what is the,
Sorry.
Yeah, yeah, yeah.
So, what is capsule network?
A capsule network is a kind of neural network. Okay, they will they will actually keep track of the presence of different patterns in the image, as well as it will keep track of the hierarchical relationship between different parts of the image, so that we can tackle the issues of the max pooling problem that I explained here.
Okay.
sir, what is the difference between using one filter and many filters in convolution operation?
Yeah, yeah, actually I forgot to explain one of the major point, sorry. See, from the explanation of convolutional neural network, you got the idea that we are tackling the patterns within the image, right? After using one convolution, we are using multiple patterns, different the presence of different patterns in the input image, right? So the question you should be arised by understand after understanding this concept is, who will define this filter? Who will define this filter? That is what you have asked, right? Are we need to use a one filter or n filters?
Yes, sir.
Yeah, we always need to
And
use
what
n.
will be the values of this filter? How the values of this filter will be designed?
Yes,
That is also I
that
want to know.
yeah, that is a major point you should keep in mind about convolutional neural network. Actually, we can fix the number of filters and the size of the filter. Okay, and the values within the filter is ultimately random at the beginning. Okay, ultimately random at the beginning. So what will
Okay.
happen? We will not be able to say what patterns are actually getting extracted from the input, right?
Yes.
Yes. So what is happening is, if you are giving the image of a dog, it will randomly extract some features, right? With the random filters, it will randomly extract some features,
Yes.
okay? And that features will be given to the fully connected layer for the classification. And if that classifier network is classifying it as a cat, what you can conclude?
It
Who
is
is
wrong.
responsible for that? The features
But
extracted from the filters as well as the weights in the fully connected layers are wrong, right?
yes.
So what is happening is, on performing the back propagation, the neural network will adjust the weights in the fully connected layers as well as it will adjust the filters.
So a kind of back propagation will be performed.
Yeah, perform to adjust the filters also.
Okay.
So
Will it
what
be
will
same
happen?
as that of artificial neural network or different back propagation
Yeah,
algorithm?
the same back propagation can be applied, but in the simple MLP, a single weight is getting updated. But in the case of CNN, it is a filter itself. It's a collection of weights for each filter.
Okay. Okay.
Okay, so what is happening? First, you will give a dog, then it will be classified as cat. Again, back propagated. The filters and the weights will get adjusted. Again, you are giving a dog, then again, it will be classified as cat with 0.5 probability, right? Again, you will adjust the weights, and now on giving a particular image of a dog, again it will classify it as cat with a probability of 0.1, right? So gradually what is happening, the weights as well as the filters are getting adjusted repeatedly in such a way that all the outputs are getting properly predicted. That is, the loss between the predicted values and the actual values should be minimal.
So one more thing, if the after one convolution operation, the output values will be fed into the fully connected layer, or many convolution
No,
operations.
no, many convolution, because
Okay.
the
So
intuition
if you are
behind.
using
Ah,
the filter, and we after if we first use the randomly chosen filter, and
yeah,
the features are some features will be extracted.
yeah,
So if that features are fed into the artificial neural network only, then it will be classified as cat or dog.
yeah.
So
So
so then
the features
but
itself is wrong, and the weights in the neural network part is also wrong, right?
yes. Okay. Oh.
So both are actually responsible for that.
Okay.
The
Okay.
wrongly extracted features, and the see, you can get the idea of convolution after each from this example. See, at the first layer, okay, at the first layer, the convolutional neural network will extract the features like this. Okay, it will understand the edges, ports, and all, right? Then after giving this as an input to the next convolution layer, it will try to find out the different parts of the objects. Okay, and after that, again, if this is given to a particular convolution layer, then again the bigger patterns will get extracted, and finally it will get extracted with the bigger patterns and concluding with a particular class. Is that clear?
Okay, sir. Okay. So we have to use one filter or many filters for the
We have to use
convolution.
and many filters, because
Okay.
one filter is capable of extracting one pattern, right?
Okay, okay. So we
So
have to use.
different patterns should be extracted with different filters.
Okay. Okay, thank you, sir.
So is
Can you
this
explain the transfer learning concept?
Can you tell me again?
Can you explain the transfer learning concept?
Transfer learning concept. Yeah, I will tell you that. See, are you able to see the input image? The image I am
Yes.
showing.
Yes.
Is it possible?
yes, yes.
Yes. Right.
Yes. Okay. So this is a typical neural network. Okay. So and this neural network is supposed to classify the image as Donald or Goofy or Tweety. Is that clear? So I will train this neural network with n number of images of Donald, Goofy, and Tweety. Is that clear? Okay. So what will happen? The convolution filters in the convolution layers as well as the weights in this fully connected layers will get adjusted.
Okay.
Okay. So what is our intuition at this point after doing all the convolution and max pooling? At this point, okay, at this point we are getting a good set of features that represents Donald, Goofy, and Tweety, and with that features our fully connected layer will be able to classify whether it is Donald or Goofy or Tweety.
Okay.
Are you clear with that?
Sir, but since the feature engineering is inherent in this, we
Yeah.
cannot identify that which feature was used to classify it
Yeah,
into the.
we that is a black box. We cannot say that which feature is used, but the features what we are getting at this point will be relevant if we are getting good classification result, right?
Yes, sir.
Yeah. So this at this point you will be getting a good set of features. That features are particularly good for identifying Donald, Goofy, and Tweety. Okay.
Okay. Okay.
So after the training process, this particular convolution filters as well as the weights will get attain a particular value which is good for classification. Okay. Now think about a situation if this neural network, okay, this neural network is trained with a large data set and we are getting good results for that. Suppose if we are getting good results for a data set with 1,000 classes. Okay, that 1,000 classes include so many animals, fishes, vegetables, vehicles, whatever it is. So many 1,000 classes are there, and you are getting a particular good accuracy for that model. So what you can actually understand from that. At this point, this network is capable of extracting good features from an input image that can be utilized for classify that image into one of the 1,000 classes, right? Yes. So what we are actually doing is, suppose we have an image, a data set. Okay, we have a data set. So usually what we will do, we will start with the random filters and weights, and on training, it will arrive at a particular set of weights and the filters, right? But as I'm not having much data for such training process, I will start from the weight which is already learned from a big data set, right? And I'm having the intuition that these weights are capable of extracting good features, right? So with that features alone, our problem, our data set can be trained on it, and we can extract the features very fastly instead of keeping starting from the random values. So the idea of transfer learning is that the model which is trained for one problem, the model which is trained for one problem can be utilized for solving another problem In three different ways. We can do feature extraction, we can do freezing, we can do fine tuning. These are the three methodologies we can use in transfer learning.
Some of the parameters are fixed and some of the parameters are being altered according to the new data set, right?
Yeah,
So
start
what
instead of
are the
starting from the initial data, instead of starting from the random weights, it will start from a learned weight on a particular data set. And we have two
all
options.
the
Yeah, we have two options. That is, we can do the pre-training. On pre-training, what we are doing is we will start from the fixed weights, then we will train the entire network again. That is one strategy. But there is another strategy called freeze and train. In freeze and train, what we will do is we will freeze all the convolutional layers, but we will actually tune the last fully connected layers. Only update the fully connected layers. That is what we are calling as freeze and tune. And one more convention is there, that is we will simply pass our data to the convolutional neural network, and we will extract the features from the flattened layers, and with that feature you can train any other meta classifier like support vector machine or KNN or some other classification models. So these are
Sir,
the
would
three.
that be a hybrid model?
Yeah, that can be a hybrid model too, that can be an ensemble model too.
Sir, what is the difference between the two?
Actually, there is the difference is that, see, the one is to extract the features and apply on a another classifier. One is to train the entire network again, and the other strategy is to keep this layers fixed and train only this part. You can actually choose according to the use case you are having.
another doubt is
Yeah.
instead of the last fully connected layer, can I use some other machine learning algorithm like
Yeah.
SVM or
Yes, that is what I said. But in that case, you are not doing any kind of training. Instead, you just pass the input here, get the output from this point, and for all the inputs, you just collect features like that. Then you can apply the machine learning techniques,
any machine learning?
any machine learning techniques.
So another question is there are several architectures, deep learning architectures,
Yeah.
and for a particular application, how do you select a suitable architecture?
Are you
How do
talking
you
about
find, or
different
how do you,
different pre-trained models?
no, the architecture means how many convolution layers, the size of the convolution
Yeah,
layers.
that is purely a do at the experiment thing, but there are some techniques which is called as grid search or random walk, and it can be implemented with a particular package called keras tuner. Keras
Oh,
tuner is there. With keras tuner you can actually optimize your number of hidden layers, number of neurons in each hidden layers and all. There is a package like this.
any scientific way of finding this,
The
or
sign, the, it's actually an
it's
NP
like
complete problem. If you think of that in a scientific way, it is an NP complete problem. There is no way to exactly find out the optimal solution, but we can do some kind of meta heuristics searches like random forest or grid search to find the near optimum configuration of our neural network.
okay, thank you.
Yeah.
So is this automatic feature extraction is very specific to images using convolutional neural network? For example, in the case of sound data classification, can we
Yeah.
extract the features automatically?
Yeah, actually, for that, you just need to understand what are the types of data we usually handle. Usually, in all computational problems, we use two different type of data, which is called as spatial data as well as temporal data. The data with the spatial dynamics and the data with temporal dynamics. The spatial dynamics is like, I can show you one example. To give you more clarity on the explanation. So I just avoided that part yesterday as we are having less time. See, can you see this? Is my screen visible?
Yes.
Yeah. See, this is a collection of pixels. Okay, there are 284 pixels. Okay, and each of the pixel is holding some kind of value, right? But are you getting any kind of information from this representation? With this 784 pixels, you are having the entire 784 pixels, but you are not getting any kind of information from this, right? But if you arrange the 784 pixels like this, a 28 by 28 grid, the entire thing is conveying some kind of information, right? This is called as spatial data. That is, the unit informations need to be arranged in a row column manner to get the entire information. That is, the relationship between the neighboring pixels are important. The neighboring unit informations are important. Then, in a spatial way, then it is called as a spatial data. Is that clear?
Yes. Yes.
For such kind of data, the convolution can be utilized for finding the correlation between the patterns present in it. Okay, but can you just think of this? If I tell you I'm telling about a sentence, or I have uttered a sentence, and that word contains terrorism, I, India, hate, and then love. Is it? Can you tell me whether it is a positive sentence or a negative sentence? Is it possible? If I say like I love India and hate terrorism, this is a positive thing, and I love terrorism and I hate India, that is a negative thing, right? So here, instead of spatial arrangement, the time dependent arrangement of the data is important. The temporal arrangement of the data, or the temporal dynamics of the data, is important, right? To get the context of a particular information, you need to get what is actually comes before and after the particular element. So such kind of information are called as temporal data, and in some time there are data called spatio-temporal data too. In spatio-temporal data, see, consider, suppose you are entering into your living room, and one of the movies got posed in the TV, and you can see a scene that two persons are there. One person is having a knife in his belly, and one person is holding the knife. Will you be able to tell me that person holding that knife is a culprit or a savior? Is it possible?
Not possible.
Not possible. There we need the scenes before and after that scene, right? So we need the temporal data as well as the entire information from the screen is also important. The scene is also important. Such kind of data is actually called as spatio-temporal data. So for this temporal dynamics, we are always using a particular architecture called recurrent neural network. So the temporal dynamics can be automatically extracted with the help of the recurrent neural networks. So the spatial dynamics with convolutional neural networks, and the temporal with recurrent neural networks. I think you are getting more information regarding recurrent neural networks in the coming classes. So audio is particularly a temporal data. So you can handle that with recurrent neural networks, and some other cross-platform techniques are there. You can actually convert this audio from time domain to frequency domain. Then after converting it into frequency domain, you can consider it as a spatial data. Then you can handle with the convolutional neural networks too.
Thank
Is it clear now?
Yeah, clear, clear.
Anything else?
Sir, one more doubt, sir. Generally, when we go for any presentation
Yeah,
as a scholar, because all these algorithms, whatever we are learning, all these algorithms are predefined.
yeah.
So if we have a classification like dog or cat, some classification, if we are trying to do using these algorithms,
Okay.
generally the question what we are facing is what is the novelty in your work?
Yes, exactly.
So in what way we can support ourselves because the work what we have done, because we can't change the algorithm, no sir.
Yeah, but we there are a lot of techniques, uh, or there are a lot of ways we can come up with novelty. Okay, like see, I can show you one architecture. One of our recent works is there. Uh, See, have you heard about different architectures in neural networks? Like,
Alexa,
that they are all pre-trained models, right?
yes sir.
Yeah. But see, suppose, see, uh, suppose you are using a convolutional neural network for a classification task, okay?
Yes sir.
And it is particularly extracting different spatial patterns, right?
Hmm.
Okay. So as I said, there is a problem of the hierarchical relationship is maintained within the images, right?
Hmm.
So how can you tackle that? You need to use the convolution, and you need to tackle that issue too. Okay. So
Okay
you
sir.
can think about an architecture like, see, this is particularly called as a feature fusion. That is, you have you have an architecture like this. Okay, you have a data set. Okay,
Hmm.
usually what we are doing is, see, we will apply this on a CNN, right?
Yes sir.
This can be VGG16 or whatever, ResNet or whatever it is.
Yes sir.
Then instead of training this model, you can just extract the features here.
Okay sir.
Okay, so the spatial features are getting extracted from here, right?
Yes sir.
Then you can apply the same thing on a vision transformers, which will apply the attention kind of techniques
Hmm.
to extract the features. So here we have the correlation features, as well as here we have the attention based features, right?
Okay sir.
What you can do is you can concatenate this. Okay,
Hmm.
then there is a feature fusion is happening. With this feature fusion, usually what we will do, we can go for a classifier, support vector machine and all, right? But instead what you can do is you can create an ensemble of classifiers. You can use SVM here, you can use KNN here, you
Hmm.
can use a random forest here, right?
Hmm. Yes
So
sir.
do you feel it as a novelty?
Yes sir.
Yes. And
Yes sir.
sometime after fusing these features, the number of features will be very high, right?
Yes, sir.
So this kind of models cannot handle this. So what you can do is you can bypass this with a particular feature selection method.
Sir,
Okay.
PCA can be applied here.
PCA won't work actually, because if the number of features are very high and the data set is very high, the PCA will struggle to extract the features. So what you can do is
Then,
you can use the uh, gain based feature selection methods. Okay, the extra tree classifier and select front model methods can be used. Then you can apply this for the uh, support vector machine and all, or even if you can use the explainable models. Okay,
Okay. Hmm.
explainable models, right? So likewise, you can think of novel things and create it with uh, new hybrid models and check for the goodness of that model. If it is giving better results, you can actually publish it as or propose it as a good work.
Okay, sir. Means we need to see the combination of algorithms that we can apply and get the
Better
novel.
result. Even you can think about the mathematical aspects inside the network.
Okay,
sir,
sir.
any suggestions regarding altering any existing algorithm itself?
Yeah, we can do a lot of things. For the purpose. What is the purpose? Is it for classification or something?
Yes, sir. For classification
Yeah,
only,
yeah.
multi-class classification.
Actually, we have a paper like this. Uh, Big data classification, genetic algorithm.
Sir, optimized selection of features can also be one of the points, na?
Yeah,
Where we first go for
that you can.
optimization and then we go for using the this deep neural networks or something
Yeah,
like.
that is a possible thing. See, this is one of our work. This is a very unconventional work. See, what we have done is, see, can you just see the title of this work?
Yes, sir.
A new novel neural network model, okay, with distributed evolutionary approaches for big data classification. Okay, so what we have done is, see, uh, as we are handling the big data, the data will be distributed, right? Okay, so instead of back propagation, what we have done is we have used the genetic algorithm to find the optimal weights within the neural network. And what one of the major property of this genetic algorithm is it is highly parallelizable. So that parallelizable architecture can be implemented over the big data architecture like Hadoop and all. So internally, you can modify such kind of algorithms with changing the optimization techniques. So people are actually working on different optimization functions, loss functions, and all.
So can you please share your research paper link?
Yeah, yeah, sure. For this paper,
Yeah, yes, sir.
and most of the time, I am working with the domain called culture, heritage, and art computing, and I'm working with the data set like dance, music, historical monuments, and some other traditional art forms in Kerala. And as well as I'm doing some kind of theoretical works with quantum algorithms like topological data analytics.
Sir, for
So
the
can you?
medical image classification where the data is very, very correlated, uh,
Yeah,
any suggestions regarding going for such kind of work where it's very, very difficult to visually identify the
yeah.
differences
Actually, you can
between.
use some kind of mathematical transformations, which will clearly distinguish some kind, or which where we can apply some kind of projections, mathematical projections on the data. Then the minute differences in the inputs will get highlighted more. So after converting it into such kind of unconventional spaces, you can then apply the traditional techniques to effectively classify or extract the features like that.
Thank you, sir.
Sir, can you please guide on which are the good areas for research in deep learning?
Now, and are you working with images or text?
Sorry, sir.
Are you working with images or text?
Sir, both, combination of both, image recognition and voice recognition, both.
Yeah, if we are going for images and all, the diffusion networks, even the object detection modules, segmentation algorithms are the good choices. And for text, now the LLMs are there. A lot of works are happening in RAG, the prompt engineering, fine tuning methodologies. And even if you want to apply, if you want to do an applied deep learning research, you can
Hmm.
actually go for information retrieval systems, where we can
Yes, sir, applied.
very effectively use the deep learning techniques like image captioning, text generation, image generation kind of stuffs for different variety of applications.
Sir, can you please share your contacts, like email contact, where we can get in touch with you regarding any
Yes,
guidance for research or
yes, you can go to the QSAT website. You can get the contacts from there. Kochi University of Science and Technology, QSAT. You can search for us. Or I have shared a PPT yesterday, right? I hope you got it.
sir? No, sir, we haven't got.
I have shared
I
it.
mean,
I
after
think
session, yeah,
the organizers will share that. Within
okay.
that, I have my contacts.
Sure, sir. Sir, and previously you told for some problem statement that we need to increase the number of neurons in with respect to that deep learning problem. So,
Yeah.
but will it affect the CPU computation power? Like, if there is not much capacity to hold that CPU computation power, like increasing the number of neurons, will it affect the computation time as well as the
Yes.
CPU efficiency?
Yes. Yes. It will definitely affect. But usually these kind of things are done for big problems. Most of the problems we are actually handling is not much complex, right? See,
Yes, sir.
if you look into different architectures that are published with ImageNet dataset, like
Hmm.
VGG16, ResNet, they're all very big architectures.
Yeah.
Even hundreds of layers are there. That will
Hmm.
definitely, as the problem is getting more complex, definitely we need to go for such kind of big architectures.
Sir, but just curious, just to know, I'm curious that instead of increasing the number of layers, can we use certain hypertuning parameters like learning rates,
But
epochs,
there is a
and
limitation for that.
oh, okay,
Yeah, because the tuning parameters and everything is actually accelerate the training time and all, but it will not work with accuracy.
so for accuracy, what are the main factors we need to focus on?
Yeah,
Like
most of the time the accuracy is lacking due to the more complex decision boundaries. So
like
definitely
PCA.
no, like suppose if you are having a class, okay, a
Yeah,
heterogeneous classification problem, like you want to classify a set of objects into birds and furnitures, okay,
multi-class, like
birds and furnitures, okay.
okay.
That, just think about the variance of data within that furnitures.
Mm-hmm.
Is it a wide variance, right?
Yeah,
And in the case of birds also, if you simply take the birds as a class, the variety of appearance of birds is actually very high, right?
yes.
So they need if the model need to generalize such kind of complex high variance problems,
Mm-hmm.
definitely they should go through the large number of layers.
Okay, understood. And sir, with respect to I mean, everything will be based on the core pattern recognition, correct?
Yeah,
Like for feature engineering. So even before we try to apply those tuning parameters or increase the number of layers, before that we have to, as you yesterday told that you need to pre-process the data. In
Yes, sir.
yesterday's
Yes.
lecture, you showed
Yeah,
the pipeline.
there is a convention called data-centric approaches. Instead of making the models complex, we can actually work on the data itself. Okay, do proper kind of normalizations, pre-processing, data cleaning, then that will give good results actually.
So how can we decide which are the best approaches or some algorithms with respect to either deep learning or any based on the given problem statement we are trying to solve?
Yeah, that is an uncertain situation actually, because the primary assumption of machine learning is that no algorithm will work well for all the data, and no data will give better results on all the algorithms. Okay, so as a machine learning engineer, you have to find the best combination of data and the algorithm which works well, and also the hyperparameters.
Okay, sir. Thank you, sir.
Sir, I have a question.
Yeah.
So this is regarding the convolution neural networks
Okay.
and its correlation with the live stream data. That is, the images are let us say per minute the images or the number of images would be I mean say some set a limit on it. So
Okay.
how to use that? I mean, will the same model that we developed or available can be inherited for this?
So, sir, I just want to ask you, what is the task you have to do? Like, is it object detection, or is it a classification, or is it an anomaly detection? What is the purpose of the model?
Let us say object detection on image that we developed a model, and
Okay.
can we use the same model for a live stream data?
Yeah, definitely we can use that for a live streaming technique. But you have to work on the inference time instead of training time. You have to concentrate on the inference time.
Okay,
The inference time should be less, as the live streaming data will be captured in 30 frames per second, or more than that, right?
yes,
And it should be again rendered in that speed. So if our model is taking much time to detect the objects within an image,
okay,
what will happen is it will make a lag. It will make a latency in it.
okay,
So the inference time is very important. That is what is improving in the newer versions of YOLO.
okay,
The main focus they are giving is the inference time, or
okay,
to reduce the latency. And there are a lot of other things that you can do. Instead of taking all the frames in a second, you can choose the significant frames
okay,
for the inference part.
okay, okay,
Because in a second, or in a 2 or 3 seconds, there won't be much change in the captured image, right?
yes, yes,
So you can use some kind of keyframe choosing algorithms for choosing
okay,
the keyframes, and that keyframe can be given to the object detection.
okay,
So only we need to infer the or perform the object detection once in a while. A big change in the keyframe is happening.
okay, okay,
Such
got it,
such
sir,
kind
got
of
it.
method can be done.
Okay, sir, got it, got it. Thank you, sir.
Yeah.
So, shall I wind up? Shall we wind up this session, sir?
Yeah, yeah, sure.
So,
If no other questions, we can wind up.
okay. So, now I invite Ms. Shefna Naushad, Assistant Professor, Department of Computer Engineering, College of Engineering, Chertala, to propose the vote of thanks.
And
Thank
ma'am,
you,
I would
ma'am.
like to get some reviews from the participants too, because we are not
Thanks
seeing them.
for the wonderful session, sir. Thank you.
Thank you, sir. Thank you very much. Actually, we have so many questions, but time is limited. We are unable to ask. Definitely, we will contact you in with you, sir. Uh,
You're always welcome to
Thank you so
QSAT.
much for a wonderful. Thank you so much, sir. Thank you for the wonderful sessions and clarifying our doubts with your patience. It is very much helpful for us, sir. Thank you.
Yes, sir. Thank you so much, sir. It was a wonderful session.
So, is there any other feedback? Shall we move on to the word of thanks
Yes,
session?
yes, yes.
Okay. Diploma,
Okay.
please join.
Okay. On behalf of the organizing committee and all the participants, I would like to extend our heartfelt gratitude to you for delivering a highly informative and engaging a session on mathematical building blocks of ANN and image analysis using deep learning during our FDP Day 2. Your unique ability to simplify complex concepts starting from the fundamentals of a line equation and bivariate functions and gradually building up to perceptrons and gradient were truly impressive. The participants were thoroughly engrossed throughout your session, and your explanation sparked a renewed interest in the field of machine learning and deep learning. Your expertise and passion for AI were evident throughout the session, and we are very grateful for the time and effort you invested in preparing and delivering this session. Your contribution to our FDP has been invaluable, sir, and we are confident that the knowledge and insights gained from your session will have a lasting impact on our participants. Once again, we thank you for your understanding contribution to our FDP. We wish you all the best for your future endeavors and look forward to your continued contributions to the field of ASR. Thank you so much and thank you all.
Thank you. Thank you for the input.
Thank you, ma'am. So, thank you all for an engaging and productive second day of our 6-day faculty development program. We hope you found today's sessions very informative and encouraging and enlightening. So, we are grateful for your active participation and thoughtful questions. So, we will reconvene tomorrow, ready to explore new ideas and insights. Thank you all and wish you all good night. Thank you.
Thank you, ma'am. Thank you, sir, for this wonderful session.
Thank you, ma'am.
Thank you,
You're
ma'am. Thank you,
welcome.
sir.
So, the attendance link and feedback link has been shared in the Google Meet chat box. Please ensure attendance. Thank you all.